So each reaction that we did on Tuesday was indicative of a different type of reaction. Combustion.
Single something, double something.
Single and double something. Yeah, that's right. So we'll list them. I'll give you kind of the general form and then an example. And the reason that we categorize reactions into types like this is because it helps us predict the products. There are some questions at the end of the lab that say, like, fill in the rest of the reaction. When you can categorize a reaction in one of these types, you can figure out what the products are going to be. All right. So the first type we're going to look at is called combination, or sometimes composition. The book calls them combination. And that's when you just have two reactants that combine to form a product. So something like this. Something plus something else combines to form the product. The one that we did yesterday that's an example of that is when you heated the magnesium in oxygen, magnesium and oxygen combined to make magnesium oxide. So that was an example of a combination reaction. Multiple reactants, one product. By the way, we should also say not all chemical reactions fit nicely into one of these categories, but the ones that do, we can predict the products because we know what they're going to do. Combination reactions are pretty easy to predict, but you have to know that it's a combination reaction. So if you just randomly see some reactants, you don't necessarily know that they're just going to combine. The only time that you know that pretty much for sure is if you've got two elements, because there's really no other way those two things can combine. You're going to put that, you got Mg, you got O, you're going to put them together. You got to figure out the ratio, but you're going to put them together. Second one is kind of the opposite, and that's called decomposition. In decomposition, it's kind of the opposite. You start with one thing and then it breaks apart into other things. So you start with some compound like AB, and then it decomposes into A and B. The one we did on Tuesday that was this type was the calcium carbonate. So calcium carbonate decomposed to make calcium oxide and carbon dioxide. These are really hard to predict because you might know that it's a decomposition because it just has one thing. This is the only type of reaction that just starts with one thing. But it's hard to know exactly how it's going to split up. Like, why is it CaO and CO2? Why isn't it Ca and CO2? Or some other combination, or CaC and O2. There's various ways that could decompose, and it's not easy to figure that out necessarily. So just seeing the reactants doesn't give you enough information to predict the products in these kinds of reactions. And then we get to the next category, which are the easiest to predict, or some of the easiest to predict, the replacement reactions, or we call them substitution, or I think the book says replacement, so we'll use that. Where you've got one compound and an element, or two compounds, and they kind of switch places, switch partners. We did those yesterday too. There's two types of these, so we'll look at both of them. First is the single replacement. So I made a draw an E there. And then we'll look at the double replacement. The single replacement is what we did with the dropping the metal pieces into the acid. So we have, in the general form of this one, you have some compound that reacts with some individual element. And the element replaces one part of the compound, and then that part goes off on its own. So you have like Cb plus A. In this case, the C takes the place of the A, whatever that is. So the one we did on Tuesday that's like this is HCl, that's our compound, plus some metal like magnesium. And the magnesium takes the place of the H to make magnesium chloride. And then the H ends up on its own, but H on its own is always H2 because that's one of the diatomic molecules. So one thing with these is, yes, you can use them to predict the products, but you still have to build new compounds. You can say, I know the magnesium is going to go with the chloride, but they're not going to be in the same ratio. It's not just going to be the Mg and the Cl together, because we have to have it be MgCl2 to balance the charges properly. This equation isn't balanced. Yeah.
Would it still be considered a single replacement instead of CD plus A? It would be like C.
Yep. So it just replaces one part. It just depends. Most reactions like this, it's the cation or the metal kind of part that's being replaced. I think that's it. We just put a 2 there and then it's good. Okay, the other part is the double replacement. This thing doesn't want to write today. In double replacement, you have two compounds, usually ionic compounds, that switch partners. So the cation from one goes with the anion from the other. We think of that as AB plus CD. We usually write our cations first, so we're assuming in this example that the A and the C are the cations and B and D are the anions. So they're going to switch places. A is going to end up with D, and then C is going to end up with B. And that maybe doesn't make sense in the abstract, but let's look at an actual example that you did yesterday, where you reacted cobalt, was it nitrate? Cobalt nitrate yesterday or Tuesday? Anybody remember? Cobalt nitrate, cobalt chloride. It was what? Yes, it was pink. Does anybody remember what compound it was? You think it was nitrate? I think it was nitrate too. Yeah, cobalt 2 nitrate. So that's an AB kind of thing because it's got cobalt and it's got nitrate. Even though there's multiple atoms in there, there's nitrogen and oxygen, we think of that as a kind of a binary compound, two things, the cation, the anion. And then you reacted that with a few different things, but one of them was NaOH, also an ionic compound, a cation and an anion. So then in the products of a double replacement, the cobalt from the first compound goes with the hydroxide from the second compound. The sodium from the second compound goes with the nitrate from the first compound. But we have to refigure the ratios because COOH is not the right combination. Cobalt is +2, nitrate or hydroxide is -1. So we have to balance that properly. So the product between cobalt and hydroxide is COOH2. And the product between sodium and nitrate is Na and NO3. Then we have to balance the equation. So those are the basic main types. There's one more we're going to look at, and then we'll talk about some other stuff. And the last one is combustion. Combustion is most kind of generally defined as just the reaction of something with oxygen, but we use it more specifically to just refer to carbon-containing compounds, hydrocarbons, fossil fuels, that kind of stuff, reacting with oxygen. So this one doesn't really have a general ABC kind of formula because it only applies to one class of compounds. So we have some general CHO type compound. So some molecule that's made up of carbon and hydrogen or carbon, hydrogen, and oxygen. Doesn't have to be all three. So, the O1 could be 0. And that's going to react with oxygen. And combustion always results in the same products, carbon dioxide and water. So whether you're burning wood or you're burning fuel or you're burning whatever, your products are always CO2 and H2O. So you don't have to use the starting reactants to figure out what the products are going to be. Once you know it's a combustion reaction, the products are always the same, CO2 and H2O. So one thing we can do with this is we can categorize reactions, just put them into categories. But the more interesting thing is predicting reactions, trying to figure out what's going to happen by combining these, or by figuring out where these things fit. So let me show you an example. I've got potassium sulfate and barium chloride. So before this, I would have given you the whole sentence for the reaction. Potassium sulfate reacts with barium chloride and forms whatever. Now we can try to fit this into a category and predict our own products. So the first question then is, which category does this fit in? It's a double replacement. How do you know? You're right. Yeah. Right, you've got two ionic compounds. Each one's made of a cation and an anion. And the only class of reactions that happens in is the double replacements. So in order to find the products, we're going to switch their places. And I think in this case, it's actually easier to do it with the names than with what you see there. So let's write the names of these compounds. This one is potassium sulfate, and this one is barium chloride. So then to find the products, we're going to switch cations and anions. So the potassium is going to go with the chloride, and the barium is going to go with the sulfate. The reason I did it with words is because if you do it with formulas, it's really easy to just say, oh, okay, the K2 goes with the Cl2, and I get K2Cl2. But that's not right, because the formula for the compound between potassium and chloride isn't K2Cl2. Anybody know what it is? KCl. So if you just did it from the formulas, it's easy to get the wrong thing. If you do it from the names, then it reminds you that you have to actually rebuild these compounds. So let's write the new names that we've come up with from those connections. Potassium chloride is one. And the other one is barium sulfate. Then we can build those compounds as we know how from back in chapter 6. Potassium chloride is KCl. Barium sulfate is BaSO4, since barium is +2 and sulfate is -2. And then we finish up by balancing the equation. So in some cases, we can predict the products. It's fairly limited. You can't predict all reactions using this technique, but you can get some of them. Let's try another one. CH4 plus O2. What category does that fit in? You go back and look at those. What? It kind of looks like a single replacement. It's not though. Why not? Yeah, how do you know? It's combustion. It's not single replacement. How do you know? Right, because the carbon-hydrogen thing, that tells you that it's going to be combustion. The single replacement usually only goes for ionic compounds and acids. So the fact that this is a carbon-hydrogen type compound tells us it's combustion. So once we identify it as combustion, what are the products? Yeah, right, always the same. Carbon dioxide and water. So then we can balance this, and we've got a full equation. So the point of doing these types of reactions is sometimes you can use them to actually predict products. I wouldn't worry too much about this. The next exam, the equation stuff, is mostly focused on the writing the equations, balancing them, and the mole calculations. The predicting reactions thing is tough, and I might put a question or something on the exam, but it won't be a big part of it. Okay, those are the categories of reactions, but there's a couple other things about reactions that we need to know. There's another category that reactions can go in called oxidation reduction. Also known as redox, just for short. It's not its own separate category, like it doesn't belong in the list with the other ones, because a lot of the other ones are also redox reactions. So it's something that some reactions are and other ones aren't. And it's any reaction involving electron transfer, meaning that instead of just atoms connecting or ions connecting and disconnecting, you're actually changing the electrons. You're taking electrons from one thing and putting them somewhere else. So that we can classify reactions in two groups by either being redox, where electrons move, or non-redox, where electrons don't move. There's all kinds of rules. If you go on to chemistry, you'll learn all this stuff about how to calculate oxidation states. We're not going to do that here. What we are going to do is be able to identify these by looking at a change in charge. Because if electrons are transferring, that means that charge must be changing. And that's not 100% true, because of a couple reasons. It's actually oxidation state that's changing, but we can think of it as electron moving means charge is changing. So for instance, some of the reactions we've already seen would fall in this category, like this one. So how do we know that this is an oxidation reduction reaction? How do we know electrons move? We know because some of the atoms here change charges. Does anybody see an atom that changes its charge over the course of this reaction? In other words, it has a different charge on the left than on the right. It's actually not chloride, but good guess. Everything else does, though. But yeah, it's magnesium is the one that we can see here. And the way that we see that is that we know in MgCl2 over on the right, what's the charge of magnesium? Right here. Plus 2, right. What's the charge on magnesium on the left? It's not. It's not. What?
She's like, why?
Yeah, why? What is it? What is it? No charge, exactly. So that's a different charge, right? It's 0 on the left. It's all by itself. See, that's the chemistry magic. You just like throw stuff out there and it ends up being right. What?
More confusion.
More confusion? Yeah. No, this goes way back to that, I mean, many chapters ago. We said that individual elements, their atoms have to be balanced. Protons and electrons have to balance out. They have to have the same number of both because they have to have a neutral charge. And that's exactly what we see here. An atom that's all by itself, an element that's all by itself is always going to have a neutral charge. So in this reaction, the magnesium has gone from being neutral to being +2. What does that mean about its electrons? Did it lose electrons or did it gain electrons? It lost electrons because it went from neutral to positive. So it must have lost some of those negative electrons. Losing electrons is called oxidation, and that's an example of a redox reaction or an oxidation reduction reaction. So let's define those terms here. Oxidation is when you lose electrons. Reduction is when you gain electrons. So in this reaction, the magnesium has lost electrons. The hydrogen has actually gained electrons, but we didn't really talk about how you figure that out. The key here is that when you see an individual element by itself on one side of a reaction, and it's in a compound on the other side of the reaction, that's your clue that this is a redox reaction. Because anything by itself is 0. So if it's by itself on one side and it's not by itself on the other side, that's got to be a redox reaction. That's even true when you can't calculate the charges very easily. Like this reaction here. These aren't ionic compounds. It doesn't really make sense to calculate the charges. But we can still say that we've got oxygen on the left by itself and oxygen and compounds on the right. So I would still count this as a redox reaction, as an oxidation reduction reaction. We can't very easily track the charges. That's something we can do in a different class, but we can still say that this fits in that category because we have an element all by itself, not by itself on the other side. This also applies when so let's look at the opposite before we get to something else. Let's go back up to this reaction right here in the middle, this K2SO4 right here. Ionic reactions, double replacement reactions usually, where the ions are switching places, are not redox reactions. You see how everything's kind of stays the same throughout the reaction? They change partners, but potassium is still +1 in both cases, barium still +2, sulfate's still -2, chloride's still -1. None of the charges have changed. So that means that no electrons are changing places. The ions are rearranging to be with different partners, but the electrons aren't changing. And so that tells us that this is not a redox reaction. Everything's keeping its same charge. So to sum this up then, look for pure elements like magnesium in this one or hydrogen in this one. If you see pure elements on one side, it's got to be a redox reaction because pure elements are neutral, elements and compounds are not neutral. So if you see the pure elements, you know it's a redox reaction. You know you can identify it that way. All right, last thing we're going to look at today is, and we did this a little bit before, but energy in chemical reactions. So do you remember back in lab 3, you did a reaction that got hot and then you did a reaction that got cold, and it asked you like which side of the equation you would put the heat on? So that's something we could do. We don't usually draw heat in this reaction, but we could. We could put heat on one side or the other depending on what happens. One way that we track that is in something called a reaction progress diagram or a reaction coordinate diagram. And it's a kind of a graph where the x-axis we can say is the reaction progress, meaning that on the left is the beginning of the reaction, and on the right is the end of the reaction. And then on the y-axis, we have energy. And we don't need to have units or anything. It's mostly just for shapes and to kind of look at it qualitatively, what we see. So a graph might look like this. Let's think about what that means. First of all, where are the reactants in this diagram? If we wanted to plot what are the energy level of the reactants, where is that in the diagram? If the reaction progress goes from left to right, where are the reactants? Where do we start? Left or right? Left. Okay, thank you. So yeah, so the reactants are right here. Yeah, this thing is totally not ready. There's our reactants right there at the beginning of the graph. So we would say that's the energy level of the stuff on the left side of the equation. And that means that over here are the products, the stuff on the right side of the equation. So as this reaction goes, we change energy level from where we started, and we kind of go up the hill and then drop back down. So we can learn a couple things from this diagram. First, we can look at the difference in energy between the reactants and the products. It's not exactly in the right spot, but the difference between the reactant level and the product level. Has the energy overall gone down or gone up? We just look at the beginning and the end. It's gone down. We started at a higher energy. We ended at a lower energy. So what happened to all that extra energy? We lost it. It got released. Then what type of a reaction is this a diagram for? An endothermic reaction or an exothermic reaction? Exo, right, because the energy of the actual chemicals went down, so the excess energy got released. Exothermic because the energy is released. What would an endothermic version of this look like? How would it be different? Yeah, just those two spots would be shifted. So the products would be higher energy than the reactants, showing the energy had to go in to complete this. The other thing we get from this diagram, the other part of this, is this hump in the middle. So this is telling us, if we track the energy level of this reaction, that as the reaction gets started, we actually have to put energy in order for the energy to be released. Why is that? If it's an exothermic reaction, why do we have to put energy in? It's not the same as the stuff that comes out. It's called the activation energy. And it's the energy that you need to put in just to get the thing started, to get the molecules to react. So a combustion reaction, for example. This is hexane and oxygen, so this is like burning fossil fuels. We know this is a really exothermic reaction. You burn fuel, it gives off a bunch of heat, right? But what happens when the fuel is just sitting in the air? Does it do this reaction on its own? Or what do you have to do? Yeah, what do you have to do to get like gasoline to burn? Heat it and also light it, right? So you have to give it some energy first to get it started, and then it can go do the other stuff. And so that's also a feature of reactions, is that sometimes you have to put energy in. So before we go, one last term. What does a catalyst do? Do we know in a reaction? What? We usually think of a catalyst as something that speeds up the reaction, kind of like gets it going. But the better definition of it is something that lowers the activation energy. So if this were a regular reaction, if we add a catalyst, we might be able to do the same reaction with less activation energy. And so we could do it at a lower temperature, or we could do it faster. And this is how enzymes work in the body. The enzymes are catalysts that lower the activation energy of biological processes. Otherwise, you'd need to be too hot to get them done, and you'd burn everything. So the enzymes allow you to do these processes without super high temperatures. We're out of time. I just want to give you a note in your studying. So look at other ways to speed up reactions. Specifically, looking at temperature and concentration of reactants. So that's at the end of chapter 7, looking at the rate of reactions and the things that affect it. So just take a look at those things, and I will see you on Tuesday. So quiz-wise, let's have another quiz next Thursday. I guess that makes sense. On the stuff from this week. So moles and reactions and, yeah, types of reactions. It'll be fun. That'll be quiz number 5.